In this lesson, we are going to derive the 3 laws of logarithms. And I know you saw these last year, and they were probably derived last year, but we're going to do it again because they are so very important in working with logarithms. And the derivations are really pretty simple. So we'll start with the first one here. We're going to start off by letting x be equal to log to the base a of capital A, and y is log to the base a of capital B. So I can rewrite these expressions as exponentials, which means instead of log to the base a of a, I have little a to the x is equal to capital A, and little a raised to an exponent of y is equal to capital B. Then I'm going to take the product of capital A and capital B. A times B. That's the same as a to the x times a to the y. I can use my monomial rules, and when I have powers of the same base, I'm going to add the exponents. So a times b is equal to a raised to an exponent of x plus y. Now, what I want to do is bring the log properties into this. So I can take the logarithm of both sides, and what I'm going to do is take the log to the base a of both sides. So log to the base a of a times b, that's going to be equal to log to the base a of a to the x plus y. This is a property from yesterday. Log to the base a of a to the exponent is going to be equal to the exponent itself. So we have log to the base a of a times b is equal to x plus y. So if you look at that, I want to replace x and y with a logarithmic expression. We come all the way back to the top, and x is equal to this, and y is equal to log the base a times b. So this is going to lead me to my first law, which I'm going to write next to here in red. So here's the meat. When I replace the x and the y, here's what I end up with. Log to the base a of a times b is equal to log to the base a of a plus log to the base a of b. That's the first law. So this is so important, we're going to write it again. The first law of logarithms is the product law. Log to the base a of a product, a times b. That's equal to the sum of the individual logarithms. Log to the base a of a plus log to the base a of b. That's the first law. So what that means is, if I have an argument that is nothing but products, I can break that out into separate logarithms and add them together. Because remember, logarithms are exponents. If you're multiplying powers of the same base, you add the exponents, and that's why it works. So here's an example. I want to simplify, which means I want to write in terms of a single logarithm, log to the base 3 of x plus log to the base 3 of 4x. So I have the same base, and I have some arguments here. All I'm going to do is write this as a single logarithm using the first law. So I have the right-hand side. I'm going to create a product out of the two arguments. So my final answer would just be log to the base 3 of 4x squared, because it's the 4x times the x, and that's it. You've used the law to write that expression as a single argument. So now we're going to derive the second law. I'm going to start off again letting x equal log to the base a of a, and y is equal to log to the base a of b. That means I can again rewrite my expression in exponential form. The argument a is equal to a to the x. The argument b is equal to a to the y. This time I'm going to take the quotient. I'm going to take capital A over capital B. a over b, and if I substitute in, that means it's the same as a to the x over a to the y. Using our monomial rules, when I raise powers of the same base and I want to take their quotient, I'm going to subtract the exponents. So a divided by b is equal to base a raised to the x minus y. Once again, I'm going to take the log of both sides, log of base a of a over b. That's equal to log to the base a of x of a to the x minus y. Let me fix that. Of a to the x minus y. Once again, this is a property from yesterday. When I raise a base to an exponent and I'm taking the log of the same base, these operations cancel each other out, and I'm left with log, I'm going to come up here, the log to the base a of a over b is equal to x minus y. Now we're going to replace x with log the base a of a and y with log the base a of b. So here's the second law. Log to the base a of the quotient a over b, that's equal to log to the base a of a minus log to the base a of b. That's our second law, and it's the log of a quotient is equal to the difference of the logs of the arguments, of the individual arguments. So that is our second law, and I'll show you how to use that. If I want to expand, I can tie it in with the first law. Something like this. If I have the natural log of x, y over z, I'm going to break that apart into individual logarithms. So the first thing you do is you're going to separate with the fraction bar. Think of your order of operations. If I want to undo this, I got to separate the quotient first, and that's the second law. So step one is to say the natural log of x times y minus the natural log of z. Then I can do one more step because this is a product, and that's the first law. Natural log of x plus the natural log of y minus the natural log of z. That's how you would break that apart. So let's look at this example, because this one's slightly different and you have to be careful. Some of the biggest mistakes I see is when you have a product in the quotient of your argument. So we have to be careful. The first thing I'm going to do is break apart the fraction bar with subtraction. That's the natural log of x minus, in parentheses, well not yet, not parentheses yet, minus the natural log of y times z. Now there's two things you can do. You can leave that in parentheses. If I'm going to break this apart, the subtraction has to be taken care of. So the natural log of x minus, put it in parentheses or brackets, the natural log of y plus the natural log of z. You could leave your answer like that, or you could essentially distribute the negative, because both of them have to have a negative coefficient in front. So you have to be careful when you have a product in the quotient. So now we're going to derive the third and final law. We're going to let x equal log to the base a of a, and c is now a constant. So I'm only dealing with the one expression. If I rewrite that again, we have a to the x is equal to a. So now I'm going to raise a to a power of c. So that means I have a to the x raised to a power of c. Raising a power to a power, you multiply the exponents. So I have a to the c is equal to little base a to the c times x. Once again, I'm going to take log to the base a of a to the c, and that's equal to log to the base a of a to the cx. Using our properties, we have log to the base a of a to the c is equal to c times x. I substitute in. I know x is log the base a of a, so I'm going to replace the x with that, and we will be at our third law. So our third law states this. We have log to the base a of a raised to an exponent of c. That's equal to bringing the power down in front. C times log to the base a of a. So now we have all three laws. This is the third one. You've got to know these really, really well. I'm going to do an example here, and then we're going to spend time in class really looking at different examples and places where you could get kind of tripped up by some of these. So we'll end here with a final example. Let's expand this expression. The natural log of x squared y to the 7th times z to the 1/2. This is a product, but we also have exponents in. So the first thing I'm going to do is break up the product into addition. That's the natural log of x squared plus the natural log of y to the 7th plus the natural log of z to the 1/2. And then I'm just going to use the third law to bring the exponent down in front. Exponent down in front, exponent down in front. So my final answer is 2 times the natural log of x plus 7 times the natural log of y plus 1/2 times the natural log of z. And then in class we're going to work some more examples so you can kind of see some areas that might cause you trouble, but we will get through all of that in class.